Okay. Today, my talk title is Ancient Analysis Case Study focusing on .NET malware, which is about an ancient discovered in Taiwan this year. Quick introduction to who am I. My name is Hirokazu Murakami. I'm an analyst for Japan section of SyncHost, Taiwanese cybersecurity company. I'm also a doctoral student at Shizuoka University and a member of Tokyo Denki University Research Lab. I'm just studying about how to collect intelligence from malware. I received the JEP reverse engineering malware certification a few years ago. There are my gold papers. Today's agenda. First, I explain an overview of the case. Second, I talk about the discovered attack and my analysis flow. Third, I will talk in detail about malware analysis, which is key point in this research. Finally, I will talk about the countermeasures that I found active in response to this cyber attack. Case overview. This attack was discovered in Taiwan's financial sector in March 2023. The financial sector is an attractive target for attackers. However, this cyber attack is expected to have been conducted in other sectors as well. We detected that the malware was executed via DLL side loading as soon as we started monitoring the service. An important point is that the malware's DLL was loaded by a legitimate service, SessionEnv. Unfortunately, we are unable to determine how the malware files were delivered. The 5 times is corrected. It could have been delivered in 2021. Besides timestamps, there was no other artifacts we could find. Details of the attack and description of our investigation. This is the first alert that was triggered as soon as we started our monitoring service. This discovery was made by the automated memory forensics feature. Encrypted malware is often found in plain text in memory. However, it's difficult for an analyst to manually perform memory forensics on many endpoints. So we developed an AI system that performs memory analysis and the other artifacts analysis on all endpoints every day. This is the attack flow. It's not a cool diagram, but it was very cool diagram. SessionEnv is a service used when using multiple services. The service manager executes SessionEnv.dll when the service is started. SessionEnv.dll is a legitimate DLL that runs TSVIPSrv.dll. This is normal behavior, but TSVIPSrv.dll was replaced by malicious DL. This is believed to be used as a means of malware persistence. Attackers don't need to modify the registry, create tasks or service, or so on. So it's harder to detect. TSVIPSrv.dll is a malicious DL that deals an encrypted auto-update DL.mui file, launches SyncHost.exe, and injects the decrypted data for execution. The malicious code is built in .NET, and it contains a loader to run this .NET code from native Windows applications. Native Windows applications can execute .NET code by calling the exported functions of this DL. Auto-update.dll.mui was an encrypted file. When it's decrypted, there was information about Cobalt Strike and the SITS URL. This data was copied to shared memory. If auto-update.dll.mui is successfully decrypted, TSVIPSrv.dll will execute SyncHost.exe. SyncHost.exe is a legitimate executable, but was used as a beginning of the round attack to inject Cobalt Strike. TSVIPSrv.dll sets parameters to SyncHost.exe so that it can refer to shared memory and execute Cobalt Strike there. So how did our team hunt for this incident? In the picture, left side is forensic analysis team and right side is malware analysis team. I belong right side. First, the system detected a suspicious there by memory forensics. Our team collected suspicious files from victims' machines. Then the incident handler has them analyzed by our malware analyst 10. It's me. Second, malware analysts analyze this malware in various ways: static, dynamic, and using the background. As a result, I discovered the malware content processing by reading answer file. I also succeeded to get the file name. I gave that file name to the incident handler. Third, the forensic analyst searched the file on the victim machine. It was easy because file name and path were known. The file was provided to the malware analyst again. Plus, malware analyst analyzes these files and discovered that the Cobalt Strike and SITS URLs are decrypted and executed using the shared memory. Finally, the incident responder removed the malicious files and blocked communication to the SITS servers. There are options of surface analysis result with CFF Explorer and P Studio. We can see that this DL contains .NET code. There are good tools I already use. This is the most important code in early stage of TSVIPSvr.dll. Two file names were found to be used in the file existence check. In the picture, left side is calling function 2 times, and right upside is file existence check in the called function, and right buttons are file names. Important, if the file doesn't exist, later stage isn't performed. So I need the file to continue analysis. And I loaded the discovered alt update.dll MUI file into the Malware and continued the analysis. As a result of decryption using AES-256 ACB mode, I found suspicious data as shown in the image. In the red rectangle, maybe somebody already inside suspicious data. For example, top data is 90909090. It's instruction of no operation. It's not slide. Maybe it looks like shellcode. So we check the data, and our members found a Cobalt Strike signature in the dump data with yellow root. Also, the SITS URL was discovered from the dump data. This URL wasn't registered as a malicious by many set integers service, so was undetected by most monitoring solutions. Deep analysis of TSVIPSvr.dll. I'll present some key points regarding the analysis of TSVIPSvr.dll. I use DNSpy to analyze .NET code. DNSpy is a useful decompression tool for analyzing malware built in .NET. However, information such as function names were obfuscated. I couldn't read there. I tried using .NET deobfuscation tools. We can use default and confuser.exe unpacker version tool for .NET deobfuscation. In many cases, these tools work fine and provide readable code. However, in this case, an error occurs with these tools due to analysis. I thought the reason for this was due to a technique that produces error in memory. Our team has tried to remove code that causes error in parsing. The code that is removed must be analyzed and understood without deobfuscation. The solutions how to achieve this using DNSpy. The key steps are to start the process in the debugger, stop at the breakpoint, remove the relevant code from the module in memory, and save the result to a file. Then using that file, run the demonstration tools. Bottom side, these are YouTube video link that explain in more detail. Here's images of what I actually performed in this case. I ran the Malware using run.dll32.exe and stop at a breakpoint. Then I opened the module in memory. In the left picture, stopping process at breakpoint and right side. Right click on the module name and to show pop-up menu and click open module in memory. This is opened the module in memory. Right-click the code of the module in memory that has been opened and select Edit IL instructions from the menu. This is IL instruction view. I remove the problem code with remove instruction. In this case, left upside is call instructions are problem code. Select these instructions and right click to show pop-up menu and click remove instruction. Save this edited code to the file. In this case, I have set the options for saving as in the snapshot. Please note these checkboxes. Some checkboxes may be set off by default. I run the demonstration tool with the edited file. Some errors remain, but the demonstrated code was output. You can see red error message written by Japanese, but exactly output. I don't know detail. I run and analyze the deobfuscated code. However, the obfuscated code didn't contain the code that runs natively. So I use the term sharp.dll loader for calling .NET functions. It can be executed simply by specifying the DL file path, namespace, class name, and method name. I'll briefly explain about analysis results. When the malware is executed, the main module executed first. The main obfuscation technique is by using code with loops and switches. The code in main launches set for debugger detection. If the debugger is detected, the process resets up. This is the obfuscated original code. Comment loop by switch loop for instruction and determine the switch instruction and set parameter for next data mining. And this is the obfuscated code before here and after. Now it's very easy to read. It's a good response. This is the code that digs the debugger. If this anti-forensic code is not bypassed, we can't analyze it. Malware analysts should be aware of this. In this case, we just need to suspend the thread. That's it. Very easy. This malware changes the DL name in memory of the running malware. I don't know exact reason, but I'm guessing it was intended to fake the running program. Left side appears running as .NET. The keyword is mscore.dll. And the right side appears running as native. Keyword is ntdl.dll. So analysts may be confused. After the main function finishes, the update function is triggered. This is the code that decrypts the encrypted file and injects it as a process for execution. I already told about this earlier. In addition, please note the malware has patched the first 4 bytes of the ETW event write function. I guess this is to avoid EDR. This shows the layout of the encrypted update DL.mei file. This layout is important for creating detection rules. For example, header parameters are used by malware. Attackers can set any data. Security analysts should never include parameters here in detection rules, even if there is characteristic information, because it can be easily modified by attackers. I believe that malware analysts should analyze for such intelligence. This is how the malware decrypts the file and inject it into other process. Create target process by create process API and create shared memory by empty create section. Cobalt Strike is copied into the shared memory. The target process and shared memory can reference by NT map view of section. The target process entry point code is patched to execute the shared memory Cobalt Strike and run. This is the entry point of the patched target process. This can be attached either pro. It just jumps to shared memory and doesn't execute the original code. This is a common technique for executing the shell code in shared memory. As a result of analyzing the shared memory code, I found the C2 URL when executing the communication API. In this case, it's Internet Connect A with the parameter. Port number is 443. As a result, we know that this URL is an important parameter for malware. We check the discovered parameter with threat integers. The set is our company's original. In this case, this URL wasn't identified as a thread. By analyzing the malware, we succeed in discovering a new threat parameter. Several other parameters were found in memory. This could be used for detection. Left side looks like user agent, and right side looks like get parameter and significant characters. I'm now going to summarize the result of this malware analysis. We are able to get the C2 URL as an important IOC parameter. Also, the other related parameters will be useful as IOC. The code injection technique using shared memory was found as an important technique. And this shows the importance of investigating memory. The malware was obfuscated as a countermeasure to analyze the .NET code using the compiler. The threat of developer detection and process termination was found to evade investigation by the developer. It was discovered that malware is executed via real sideloading. This is a tactic for persistence. It was discovered using Cobalt Strike for command and control. Injecting Cobalt Strike is the most important purpose of this malware. Code injection, obfuscation, and anti-debugger are tactics for defense evasion. We are able to obtain this intelligence through forensic analysis and reverse engineering malware. This information is useful not only for detecting and responding to this attack, but also for defending against future similar attacks. I want you to know that deep analysis can provide many intelligence. Effective countermeasures against this cyber attack. The result of the analysis of this case, we consider countermeasures that are active in similar cases. About detection, antivirus and anti-malware have survived. However, encrypted malware can evade antivirus and anti-malware detection. Encrypted malware will need to decrypt in memory, so that memory forensics is one active means of discovering this. However, it's not practical to manual memory forensics many endpoints in a short time. A periodic and automatic memory forensics approach will be one effective tool. Detection based on behavioral monitoring is also an active means. The behavior of network intruders and malware is similar to achieve their ultimate goal. So, behavior monitoring is effective in the long term in detecting cyber attacks. About hunting, correlation of endpoint forensics and reverse engineering of malware was a positive impact on investigation. What's needed for good correlation? Forensic engineers need to know what can be achieved by malware analysis and ask malware analysts what information they want. Malware analysts need to discover and provide useful information for hunting as well as IOC for detection. To achieve this, malware analysts need to have a basic knowledge of forensic hunting. Teamwork is necessary to achieve these goals. What is needed to create teamwork? It's training and communication before an incident occurs. Analysts have limited time after an incident occurs. We can't run much while doing investigating. In order to hunt, information is needed. Forensic agents can't investigate non-existent data. It's important to read the necessary information for hunting. It is an important source for information as it collects information focused on hunting. You should plan how and what information you will collect and what tools you will use to investigate. Consideration and takeaways. Finally, I'll summarize today's presentation. In this case, we confirmed that DL sideloading is an effective cyber attack vector. It isn't a new technique, but I think that it is effective yet. To discover this, memory forensics and behavior monitoring are active, and forensic analysis of many endpoints using AI is useful. In this case, malware built by .NET framework was used. Analysis of malware using .NET Core framework was effective with the use of debuggers and detection tools. A good collaboration of endpoint forensics and malware analysis can help you make the right analysis and find effective solutions. Takeaways. Thank you. It's over.